Hello everybody, this is me Khalid Maharaj Malik over again with a new video today. Yesterday we have studied about Norton's theorem and Thevenin's theorem. So today we are going to take the theorem portion forth, and today we shall be studying Millman's theorem, Tellegen's theorem, and star delta transformations, etc. So starting off with it, we start with maximum power transfer theorem. As the name indicates, maximum power transfer theorem. A source fetches power to the load, as all of you know. But how much power? The maximum power is being discussed here. When does a source give maximum power to a load? We shall see the condition. The maximum power that a source gives to the load is when the internal resistance of the source is equal to the load resistance, or the resistance of the load itself. So let us see it in the context of Thevenin's theorem and Norton's theorem that we did yesterday. Okay, let us make Thevenin's equivalent circuit, which is like this. Thevenin's equivalent circuit. This is Thevenin voltage with its internal resistance Vt and Rt. This is load resistance R. This is Thevenin equivalent circuit. If we see in the context of this, if we short circuit the load, what will happen? A current will flow through this loop without the resistance of the load here present. If we short circuit it, the voltage will be short circuited voltage. Open circuit. If we open circuit this load, for example, if we do it like this, it is Thevenin's equivalent. The ends are open, and here the load has been cut off from this circuit RL. This is Vt, Rt. What will be the voltage between those 2 points? This is open circuit voltage VOC, which will be equivalent to the voltage of Thevenin's equivalent. Okay, so in the context of Thevenin's equivalent circuit, this is the source. Thevenin's equivalent circuit is the source, and this one is the load. It indicates that if Thevenin's resistance, or the internal resistance of the source RT, is equal to load resistance, then maximum power will be transferred. The formula for this is maximum power transfer is equal to V open circuit voltage, open circuit square, upon 4 times the load resistance. We can also write maximum power transfer as P max. Clear? Till here we find the maximum power transfer with respect to Thevenin's equivalent circuit. And if there is Norton equivalent circuit, we have been asked to find the maximum power transfer with respect to Norton circuit, which is like this. For example, this is a constant current source, as we did yesterday. This is Norton's resistance and this is load resistance. Is that clear? What we do, if we cut off this load resistance and short circuit this Norton resistance, if we short circuit this Norton resistance and cut off this load resistance, it will become like this. ISC will flow, short circuit current will flow because there is no resistance. It is short circuited now and the short circuit current will flow. In the context of this, maximum power, this is the source. This is what? This is source. Not original source, but original source is this much, which has an internal resistance also because it is never ideal, it is real one. Okay, the internal resistance Rn, if Rn equals to RL, then maximum power will be transferred, But here we have short circuit current, here we don't have a voltage because we have in the Norton equivalent circuit, we have a current source, a constant current source or short circuit current. Okay, so in that case, P max, in case of voltage, power is V square by R, but in case of current, the power is I square R, which is ISC square multiplied by, after derivation we will reach up to the conclusion that it is 4 times RL, or we can write it as ISC square upon 4 times GL, where G is conductance or reciprocal of resistance. What does conductance say to us? Conductance means the ability of a conductor to allow the current freely to pass through it. How much freely the conductor allows a current to pass through it, that ability of the conductor is called conductance, and it is as against to the resistance. Okay, here in case we are given Norton equivalent circuit, then P max has another formula. P max is equal to ISC square upon 4 times GL. So we have two formulas for maximum power transfer from source to load. We have two formulas, formula 1 and formula 2. The questions will be asked upon those two formulas. Note it down, then we shall move on to Millman's theorem. Okay, so wiping it out now. Millman's theorem. is applicable to a circuit like I make here under. If we have n number of voltage sources connected in parallel, say like this, let me make up to 3 only here. It can be up to n number, and this is the load resistance. This is V1. It has an internal resistance of R1. This is voltage V2. It has an internal resistance of R2. This is voltage V3 having internal resistance of R3. There can be n number of voltages in parallel before the load resistance as source. This part will form the source. This will form the source. Then this can also be made into one equivalent, because there are so many voltages in parallel. So cannot we replace those all parallel voltages into single voltage and all those internal resistances corresponding to voltages into a single resistance? Then it will form a simple circuit with the load like this. Resistance equivalent. This is load. And this is voltage equivalent. So what will be the formula for this? We shall have the formula V1 upon R1 plus V2 upon R2 plus V3 upon R3 plus and so on, whole divided by 1 upon R1 plus 1 upon R2 plus 1 upon R3 plus and so on. This will form the equivalent voltage. So till now the funda of this Millman theorem is clear, that we have to find an equivalent voltage that is formed by so many parallel voltages given in a source circuit that is connected to the load. Okay, so as to make the circuit simpler one. Why is this 1 upon R1, 1 upon R2, 1 upon R3? Because all those resistances are in parallel, and if we recall, the resistances when in parallel, they are added after reciprocating them. We have reciprocated them and then we have added them. So equivalent voltage from all those voltages will be found like this. So the formula for Millman's theorem and the diagram for it is clear. I won't write the definition part here because I have already narrated it. So you people may note it. Then we shall move forward to Tellegen's theorem, and then we shall be performing a numerical problem upon that, so that the Tellegen's theorem will be clear. This theorem and the theorem that I already did this before this, they are totally formula based, and the questions will be comparatively simpler ones. But in the case of Tellegen's theorem, the questions are a bit technical, so I will be doing a numerical problem on that. Okay, wiping it out. Tellegen's or Tellegen's theorem, whatever you narrate it. Tellegen's theorem. whenever we are called for Tellegen's theorem, a formula should strike in our mind, that summation k equals to 1 to n vk I k equals to 0. What does this mean? Summation or algebraic sum. What is V into I? V into I, voltage into current, that is power. That is summation, algebraic sum of powers. This subscript, because we have to find the power for every single part of a circuit, so the instantaneous powers will be over there. I will write instantaneous powers. Instantaneous powers in an electric circuit is always equal to 0. Algebraic sum of instantaneous powers in an electric circuit is always equal to 0. Suppose this part is source and it has a load connected to it. What does source do? Source delivers the power to the load and load absorbs that electric power. Power delivered, that is power delivered equals to power absorbed. Who delivers the power? Power is delivered by the source to the load, and who absorbs the power? Power is absorbed by the load. That is, algebraic sum of instantaneous powers in an electric circuit is always equal to 0. As much as the power the source delivers to the load, equivalent to that, quite equal to that, power is absorbed by the load itself. So how we shall illustrate this? We shall illustrate this by the virtue of a question. Okay, writing a question here. For example, we have a circuit like this. We have, for example, a 5 volt voltage source here, or say 10 volt. We have a 10 volt voltage source here with an internal resistance of 5 ohm, or say this is not the internal resistance, but this is some other resistance connected to it as a part of circuit. Let there be one resistance of 10 ohm like this, another resistance of 10 ohm like this. So we are going to illustrate Tellegen's theorem here. Let power delivered should be LHS, left hand side, and power absorbed is RHS, or right hand side. Okay. First of all, let us do one thing. Let us take this node using nodal analysis. If we take this node, the voltage here will be, potential here will be VA, potential difference between ground and this point, VA. So applying nodal analysis upon this, we get VA minus this voltage minus 10 volt divided by, what is the in between resistance? 5 ohm. What does this form? Voltage divided by, this is voltage minus voltage is voltage, divided by resistance, voltage divided by resistance, this is current. Summation of currents equals to 0 in an electrical circuit. That is the nodal analysis. plus VA minus, what is the potential of ground? 0, minus 0 divided by what is the resistance in between, that is 10 ohm, plus if we see in this branch VA, by this way we go up to the ground here, VA minus potential of ground 0 divided by what is the resistance in between, 10 ohm, is equal to 0. That is summation of currents in the electrical circuit is always 0. As much currents are entering, similar currents are exiting as well. Okay, so here we find it like this: VA upon 5 minus 10 upon 5 equal to 2 minus 2 plus VA upon 10 plus VA upon 10 equals to 0. If we take LCM of those three VC, it becomes like this: 2VA plus VA plus VA divided by, LCM becomes 10, this minus 2 goes here, equals to 2, or 4 times VA upon 10 is equal to 2, or VA is equal to 10 to the 20 divided by 4, 5 volt. So the voltage here at this point we have found is equal to 5 volt found. Okay, so what is our aim here now? We have to find the currents. Okay, if we find the current that is going in this branch of 5 ampere, current I for 5 ohm, how much is that current? That is voltage at this point 5 volt divided by, because V is equal to IR, then I is equal to V upon R from Ohm's law. 5 volt divided by, how much is the resistance? 5 ohm, 1 ampere. Using this voltage again, I for 10 dash, we write this as 10 dash, I for 10 ohm, 5 volt upon 10 ohm, 0.5 ampere. Current for 10 dash ohm, 5 volt upon 10 dash ampere, 10 dash ohm, 0.5 ampere. Okay, done up to here. So what we shall do, we shall find the powers. Okay, we have the currents. So if we find here power for P for 5 ohm, power for 5 ohm will be the the current for 5 ohm into the resistance, 1 ampere into 1 ampere into 5 ohm, 5 watt. Okay, 5 watt. Power for this 10 ohm is equal to, how much is the current for 10 ohm? 0.5 ampere. 0.5 multiplied by 10 ohm. Sorry, power is not current into resistance, but that is current square into resistance. We have to square it. It will one will always make 1 as its square. We will make it square. This will become 2.5 watt. Similarly, power for 10 dash ohm is equal to, again, 0.5 ampere for this one also, 0.5 square into 10 ohm, 2.5 watt. Then doing one more thing, adding powers for all three resistances, it becomes power 5 plus 2.5 plus 2.5, 5 plus 2.5 plus 2.5, 10 watt. Powers for all the three resistances, that is load, combined load, that is 10 watt. So power absorbed, that is power absorbed was RHS. We have found RHS. Let us see what is LHS. We have found power absorbed. This resistance, and this resistance, all the three resistances together make a load, and we have found the combined power for this total load, that is power absorbed RHS, 10 watt. So what will be the power delivered LHS? Let us find it out. What is the voltage? 10 volt. What is the current that goes into this immediate resistor that is very close to this voltage source? What is the current going into this 5 ohm? We have found it 1 ampere. Power delivered, because there is no element between this voltage source and this resistor, so the total power will be given to this immediate resistor. Power delivered is equal to 10 volt voltage into current. Power is voltage into current, P equal to VI. What is the current going into this? 1 ampere. Here it is 0.5 ampere. Here again this is 0.5 ampere. Okay, 10 volt multiplied by what is the immediate current going into this? 1 ampere. 10 watt. This is, what is this? This is power delivered. Or LHS. So is RHS 10 watt and LHS 10 watt equal? Yes. LHS equal to RHS, or power delivered is equal to power absorbed, or we can say algebraic sum of powers equal to 0, which is the proof of Tellegen's theorem. So in your competitive exam, numerical of 1 mark, against which if you may mark it wrong, then you will be deduced with the negative marking. If the question is asked, so this will be asked in this very fashion, so as to verify whether the Tellegen's theorem is accomplished or not. Okay, note this one, and then we shall move on to further. Okay, Tellegen's theorem is done. So we shall be moving on to a small topic, but very last but not the least, very important topic: star delta transformation. That is a very small topic, a formula based topic, but still very sensitive and very important from the competitive point of view. Star delta transformation. Star or Y, we write it Y or star. Y delta transformation. Suppose we have been given the resistances in this fashion. Say this is R1, R2 and R3. The point is A, point is B, and this point is C. We have to convert it into, this is what, this is a delta form. Delta is written like this. We will form it into a Y structure or star structure. This point B, point A, point B, point C. For our convenience, let us make it inverted. Wiping it out and rearranging it. Let us make it like this, so that it will be convenient for us and we will not make any mistake. This point B, point A, like this, point C, and this point B, so that it will form the symmetry as like that, point B. This is point A corresponding resistance A. This is resistance B. This is resistance corresponding to this point, point C. So if we have to find the resistances interconvertibly, how will we find? For example, if we are to find resistance R3, how will R3 be found? R3 will be found like, we will multiply those in a circular fashion, RA into RB. RA, we have to find this resistance in terms of this. What will be the equivalent of this resistance in terms of this? So R3 from here will equal to RA RB plus RB RC plus RC RA, which is a circular fashion, clockwise, divided by R3. R3 was to be appended here. R3 was to be appended here, and the opposite to that is RA. We will divide this by RA. And similarly, opposites, this numerator will be same for all R3, R1, R2, but the denominator will change accordingly, which is opposite to R3 branch here. If we consider it here, opposite to that is RA. So in case of R2, the opposite will be R divided by RB, and if we have to find R1, the denominator will be RC, the numerator will be same. Okay, if we have to find, we have found this parameter in terms of this. So if we have to find any resistance from this section in terms of that, then how will we do that? Okay, if we have to find RA, suppose, in terms of that, how will we do? We will do like this. Okay, RA is equal to, if we see RA is here in between, what are the sides of that RA? RA is quite vertical here. If it was RA here, like this here, so what are the side branches of this? Those are R2 and R1. We have to write R1, R2 divided by, that is side branches. Imagine side branches here. R1, R2 divided by all those three resistances added. R1 plus R2 plus R3. That is side branches of delta. If we have to find star resistance in terms of delta, then it will be side branches R1, R2. RA has side branches like this, R1, R2, R1, R2, divided by all the delta resistance is added. Likewise, you can find all the resistance. I have found R3 from this section and RA from this section. You can find all other resistances. So this is star delta transformation. So we conclude our today's lecture with this, and tomorrow onwards we shall be moving on to two-port networks, etc. Z parameters, hybrid parameters, etc. Okay, thank you.